Hello everyone. Myself Nitin Prakash Rao Patil. I am working as assistant professor in computer science department, Savitribai Phule University, Maharashtra. So I am going to talk about or demonstrate you one particular aspect with respect to understanding the 32-bit instruction translation to object code. To do so, I am going to show you some demonstrations. In now to achieve that particular goal of saying what exactly the object code is generated from the system side, I am going to make use of particularly Linux operating system, Ubuntu flavor, and a NASM assembler. Apart from this would be a software that we are going to use. Apart from this, for reference perspective, I'm going to make use of a combined manual available for 64 and 32-bit architectures on this link provided by Intel. This would be for 32-bit and 64-bit architectures supported by Intel. Now, if we see particularly this manual, we are going to make use of some specific pages from that manual rather to achieve that particular goal. Okay, to of translation aspect. Let me open that manual. So let us say make use of page number, say for example 36, 35, 36. Now this would be dedicatedly talking about say how exactly the instruction format should be. Okay, so Intel follows this particular format by dividing it into different 6 compartments. Instruction prefixes, opcode, mod RM, SIB, displacement, and immediate. Now, as we know that Intel supports different kinds of addressing modes. So data or whatever the set of operands that you would be having may have sometimes a scaled indexed address or probably direct or indirect address. Moreover, it may have displacement added there. Along with that, there might be an immediate data provided. Apart from this, most of the instructions used rather can have both or one or two or both the operands possibly as in a register perspective. So I'm going to mainly concentrate on the instructions which are taking say both the operands of register type. Now whenever we are talking about these different operand types, we have to see that from that Intel manual instruction format, we are going to make use of two major blocks. One block is opcode and second block is mod RM byte. Now this mod RM byte is further divided into 3 parts as it is a byte. So we are dividing that into 2, 3, 3 kinds of blocks, a number of bits. Okay, 2 bits, 3 bits, 3 bits. So first set of bits starting from the most significant bit is mod. Okay, which would be either 0, 0, 0, 1, 1, 0 or 1, 1 as they are bits. Now here register or opcode. Now if I see our instruction format that we are going to make use of would be like instruction destination comma source. Okay, so now if your source is a register, then it is going to be here. And depending upon if there is only one operand or there is something else rather, depending upon what kind of instruction you are talking, it may change. But first operand could be register or a address. Correct. So the destination address would be added here. Destination register information would be added into least significant 3-bit positions. And in middle, what are the leaving apart first two from MSB side and 3 from the LSB side. The remaining 3 would be used for your source register. Now, if I go to say page below, there is a table given for this mod RM byte. Now this is meant for the different kinds of operands they are added. Like for example, your operand possibly could be only register. So if it is register to register, then mod RM mod would be used as 1, 1. If there is 32-bit displacement added along with the register or maybe memory, then it could be 10. Same case, like if it is 8, then 0, 1. If there is no displacement added, then 0, 0. Now each of the register, if we see what are the register that you are using in operand perspectively, are given some numbers. Say for example, I'm talking about a 32-bit registers now. So the order is fixed: EAX, ECX, EDX, EBX. One can see here ESP, EBP, and ESI, EDI. Similar kind of order is written over here too: EAX, ECX, EDX, EBX, ESP, EBP, ESI, EDI. Each of the register is given some numbers. Like for example, 000 for EAX, EDX contains 010. For ESP, we are going to make use of 100. For ESI, say 110 and EDI 111. Similar numbers are here. So let me use a particular file to demonstrate this part. And I'm taking some sample code too over here. Now this is what I have written here. Like what are the registers are the number representation used in mod RM. Now, as we already said that we are going to take instructions with both the operand types to be registers. So here I have taken some sample, say 8 instructions as an a sample perspective or an example perspective to demonstrate this particular thing. So here, like if I see this is move EX comma EBX. In this case, EBX is source, EX is going to be destination. Now if I see, I have used another 3 examples with move. Now registers are different. Say ECX, EDX, ESI, ECX, EDI, EDX, and so on. I have added 4 other instructions at particular level. Now I have kept all 4 above operands as it is. Like for example, whatever I had for move EX, EBX, I'm replacing move by add EX, EBX. Same case ECX, EDX, I'm using here CMP, sub and OR. So now this instruction, when it gets translated, we will require at max 2 bytes. One is for opcode from the what we saw as an instruction format. One is for opcode, a byte, and for mod RM byte. Now, as we already said that mod RM byte would be divided into 3 parts. So let me divide this like this. So mod 2 bits, there will be source. Okay, what are the source registers are, which are for you as a second operand in this case for all the examples or the sample instruction that I added, and there would be destination again 3 bits. So let me write those all 4 combinations. So for example, EX, EBX, ECX, EDX, ESI, ECX, EDI, EDX, the ones which I used above. Now, as we are aware that for each of these instructions, as both of them are containing or all of them are containing the registers as operand, so mod would be fixed. So mod would be 1 1 for each of them. So let me write that mod. Okay, now what is the source register here? So for example, it is EBX. So if I see the number for EBX is 0 1 1. Correct. Now next for next instruction or whatever the operand order is, I am having source as EDX. So for EDX, I am having 0 1 0. For ECX, say in this case 0 0 1. And for EDX, I have 0 1 0. Okay, now let us talk about destination. Now destination is EX, so register number is 0 0 0. ECX, so it is 0 0 1. Then ESI is 1 1 0. And for EDI, we have 1 1 1. Now we got a complete byte defined. So let us write that byte in terms of 2 different nibbles. So I will combine and I will write it like this. 1 1 0 1. 1 0 0 0. So let me divide this into 2 parts. Same thing I am going to do here. So 1 1 0 1 0. Okay, 0 0 1. So let me divide this again in 2 parts. Similarly for this instruction 1 1 0 0 1. Okay, 1 1 0. So let me divide again this into 2 parts. Because we know whenever we are talking about binary to decimal, we'll be requiring say number of bit positions, and as well as we have to represent this in hex because your machine code would be written in hex form. So 1 1 0 1 0 1 1 1. Okay, so we have this. So let us write this as hex numbers. So if I pick enable, so this would be 8 plus 4 in this case. For this case, like if I see 8 plus 4 12, 12 plus 1 13. So if I talk about hex representation, so I do use D. And the second nibble is 8. So I will write 8. Now 1 1 0 1 again D. Then I have only 1 here. Correct. So then again now we have C here because 8 plus 4 12. So C 1 1 1 0. So 1 plus 8 plus 4 plus 2. 8 plus 4 12 plus 2 14. Correct. So A is 10. So as we said, D would be 13. So E would be 14. So let us write E here. Now if I see the next instruction 1101. Okay, for whatever the conversion is. So X number again is D and 0111. So 8 is not there. So 4 plus 2 plus 1, 4 plus 2, 6, 6 plus 1, 7. Now we should get these in mod RM field for each of the instruction here. So for example, the second field that I am talking about is in this case it is D8. Okay, in this case it is ECX EDX. So this would be D1. This would be CE. This would be D7. As we have taken same operand, so I will keep here D8, then D1, sorry, D1. Then I have ESI ECX, so it is CE, and then EDI EDX. EDI EDX we have written as D7. One can check this one more time. For example, each of these representation. So 1 plus 1, sorry, 8 plus 4, 12. So that's why we have taken C, 13 D. Then this to be 14. Okay, that's why we have taken E. Correct. So now we have to find out opcodes for each. So we have written mod RM byte for each of these instructions. Now we have to write opcodes for each of these. Now in Intel manual, for every instruction there are multiple operand types. So accordingly, Intel manual for every instruction had a table added there. So let us first check for move. Okay, so let us go to say M. So we have here move instruction. Now as our second operand is register, first operand can be register or memory, for example. This is what we are going to talk. So RM32, R32. Now in this table, if you see the instruction like move can have say 8-bit registers, 16 or 8-bit operand, 16-bit operand, 64-bit operand, 32-bit operand, anything possibly could be there. Correct. So for 16-bit operand, let us check. So we are saying that second operand is register. So we are talking about this. So we should see now this 89 generated for it. So for all of these, it should be 89, 89, 89, 89 for each of these 4 instructions. Now we have add. So let us try to see for add. So let us go up again, try to check with add. Again, second operand should be registered. So register 32. So this should be 01. Correct. So if I see here R32, so let us take it as 01. So it is 01 for CMP now. So let us go below and check for CMP. This is CMP. OK, now for CMP again R32. So this is 39. Correct. So this mod opcode is 39. So let me write that there. Now next instruction is sub. So let us go below again. Find out sub appropriately there. SUB. Yeah, this again second operand to be 32-bit R32. So 29. And now R. MNOPQRS. So O should be above. MNO. R. Correct. So R32 again. So we should see 09. Correct. Now when we translate this code, so what I did was, so let us save this. OK. So I'm going. What I did here is I have written a code which contains the same instructions. OK. So it is containing move EXECX. So let me show you this code here. Yeah. So if you see, this instruction contains move EX, EBX, move ECX, EDX, move ESI, ECX. OK, then EDI, EDX, then add CMP, sub and R. Fine. Now let us try to translate this. So how do I translate it? Is like this. So let me write this translation instruction. So command rather nasm -ipls32 my program name, and I want to generate a LST so as to compare what are the translation that I did through hand. Is it matching with? So let us see this ACM teaching challenge 22.lst file. Now let us try to compare here. So first instruction was move EX, EBX. We got 89D8. So 89D8. Then 89D1, 89D1, 89CE, 89CE, 89D7, 89D7. Then next instruction we had add EX, EBX. So it is 01D8, 01D8, 39D1, 39D1, 29CE, 29CE, and then lastly 09 D7, 09 D7. And that's how we get the translation done for with registers, like with the instructions having both the operands to be register. So you can, for more for more videos like this, you can visit my channel, which I added a link for it on my first page. Thank you very much.